Okay, so this video is about the degree of unsaturation of a molecule, also referred to as the index of hydrogen deficiency. Okay, so this refers to a concept called saturation. And when we talk about saturation in terms of molecules, we're talking about the number of hydrogen atoms that are attached to them. So if a molecule is considered to be saturated, it has the maximum number of hydrogen atoms attached to it, bonded to it. And if it's unsaturated, then it has less than the maximum number of hydrogen atoms attached to it. Okay, so this refers to molecules. So certain molecules can be saturated and they can be unsaturated. And this is the same meaning when we talk about saturated and unsaturated fats. Saturated fats have the full maximum number of hydrogen atoms bonded to them, whereas unsaturated fats are missing some hydrogen atoms and instead have double bonds to replace the correct number of bonds. So the index of hydrogen deficiency, which from now on we'll just call the IHD for brevity, is the number of hydrogen molecules, the number of H2s it would theoretically take to take your molecule and make it completely saturated, completely having as much hydrogen as possible. And it's just a useful bit of structural information to know if you're trying to identify an unknown compound. Okay, so this video is just going to go over the simple way to figure out the IHD if you're given some sort of a structural formula. So anytime you see an extra bond, meaning a double bond, or in the case of a triple bond, that would be like looking at two extra bonds. That means you're going to add 1 to the IHD value for a molecule. Because whenever there's a double bond, that it would be an opportunity where if you broke that double bond, you could add a hydrogen to each of the atoms involved in that double bond. So for every double bond, that means you could theoretically add 1 hydrogen to that spot. So an IHD value of 1. For every ring, you also get to add an IHD value of 1 because when you have a ring, you've got atoms connected all the way around. And if you were to break the ring apart, right where you broke it, there'd be an opportunity to add a hydrogen atom to each carbon at the end of the chain. So therefore, for every time that there's a ring, that molecule is missing 1 H2 worth of hydrogen. And then one final note is that for benzene, benzene is C6H6. So every time there is a benzene ring, so maybe I should say that, for a benzene ring, you actually have to add an IHD value of 4. And that's because while we consider this to be the real structure of benzene with the electron delocalization around the 6 carbons, if you think about it in terms of a Lewis structure, we think about it as having alternating carbon-to-carbon double bonds. So there's 3 carbon-to-carbon double bonds, each one of which gives us an IHD value of 1. And then there's also a ring, which gives us another IHD value of 1. And so combined, that gives an IHD value of 4. And if you think about it, C6, if it were going to be fully saturated, it would be an alkane. And alkanes are fully saturated. So 2N plus 2, if you have 6 carbons, you should have 14 hydrogens to be fully saturated. Well, benzene is C6H6. That means it's missing 8 hydrogens. So 8 H's is equivalent to 4 H2 molecules, which is what the IHD value refers to. How many H2 molecules would it take to turn this thing into the fully saturated, non-cyclic alkane version of itself? So you have 6 carbons, but you only have 6 hydrogens. You need 8 more hydrogens to equal the fully saturated, non-cyclic kind of alkane here. And that's equivalent to 4 H2 molecules. So we would say the IHD value is equal to 4. That would be the answer to that question. Okay. So if you look through a list of our different classes of compounds, alkenes always have values of 1 because they have 1 double bond, 1 extra bond. Alkynes have values of 2 if there's just 1 because there's 2 extra bonds. Cycloalkanes have 1 ring and therefore they give you a value of 1. Cycloalkenes would give you a value of 2 because they get 1 for the ring and 1 for the extra bond. We already mentioned how benzene gives you 4. Halogenoalkanes, they can be fully saturated, like these examples are fully saturated. The Cl just replaces an H, so this molecule has as many hydrogens as possible. Same thing goes for alcohols and ethers. The oxygen actually has no effect on the number of hydrogens that you could have. Uh, Aldehydes and ketones have one extra bond, and therefore they both have IHD values of 1. Carboxylic acids and esters also just have one extra bond, and therefore they have IHD values of 1. In these molecules, the amines have values of 0. The amides with their one extra bond here have 1, and the nitriles with their 2 extra bonds, 2. And to try one larger molecule, and we can then try the rest in class, here is a picture of ascorbic acid. And if you're trying to figure out the IHD value, first thing is count the number of extra bonds. There's 1 here, there's a second one there, and that appears to be all, so that's 2. And then there's 1 ring, which means you have to add another 1 to your IHD value. And so ascorbic acid has IHD value of 3. And so if you're given a structural formula, it's really as simple as that. Count the extra bonds and then count the rings. And if there are benzene rings, then count the benzene rings as values of 4. Sometimes you don't get structural formulas, you just get condensed formulas. And so then it's a bit more complicated to try to figure it out. I've made another video that goes over how to produce your target saturated molecule so that you can figure out the difference and therefore figure out the IHD value. But most of the time, the molecule that you're given, you'll have a structural formula. And if you just look for extra bonds and rings, then you can very quickly figure out the IHD value for any molecule.